Welcome. You know those apps you use every day without a second thought? Ever wonder what it really takes to build one from the ground up? Well, today, we're going to do just that. We're putting on our architect hats and designing the complete blueprint for a parking garage reservation system. So here's our roadmap. We're going to start at the very beginning by laying the foundation. Then we'll design the digital doorway, structure the core information, and finally, assemble the entire high-level architecture before digging into some absolutely critical trade-offs. All right, first things first. Before we write a single line of code, before we even think about a database, we have to answer the most important question. What does this thing actually need to do? This is our foundation. Get this wrong, and the entire structure will be unstable. It always starts right here by defining the requirements. And we split them into two buckets. What the user can physically do, we call those functional requirements, and the rules the system has to live by, the non-functional requirements. So let's break it down. Functionally, it's pretty straightforward, right? A user needs to be able to reserve a spot, pay for it, and of course, cancel if their plans change. But the non-functional side, that's where the real design challenges are. We need to handle different car sizes, have a clear pricing model, and this is the big one, we need high consistency. We absolutely cannot have two people booking the same spot at the same time. I mean, can you imagine the chaos? That's the kind of disaster we have to architect our way out of from day one. Okay, requirements are locked in. Now we need to design the front door to our system. This is the API, the Application Programming Interface. It's basically the set of rules for how anyone or anything can talk to our system's brain. And we're not going to have just one door, we're going to have two. First, there's a public API. These are the commands a user can directly trigger from the app, like reserve the spot. Then there's the internal API. Think of this as the behind-the-scenes stuff, the helper functions our own system uses to figure things out, like calculate how much this reservation should cost. And this table just makes it crystal clear. You see the public endpoints, /reserve, /pay, /cancel, super direct, user-driven actions. Then you see the internal ones that do the real work, /calculate payment, /free spots, /allocate spot. Keeping these separate is a great practice. It makes our whole system cleaner, more secure, and way easier to manage down the road. So we've got all this data flowing in and out through our API, but where does it all go? We need a place for it to live. It's time to design our database schema. This is literally the floor plan for our data, deciding where every piece of information is stored so we can find it again. For a system like this, a relational database, something like PostgreSQL, is just a perfect fit. And why is that? Well, because our data is highly structured. You have garages, which have spots, which get reservations. See? It all connects in a very predictable, logical way. It's not like a social media feed with random posts. This is organized. Think of it like a set of perfectly linked spreadsheets. Now, the absolute heart of our system is this table, reservations. This is what ties everything together. Every reservation gets a unique ID, and it links a specific garage ID and spot ID to a start time and end time. And of course, a little flag to tell us if it's been paid for. And next, we have the spots table. This one's simple but crucial. It just keeps track of every single parking space. Each one has an ID, it knows which garage it's in, what size car can fit in it, and its current status. Is it free? Is it taken? Or is it maybe blocked off for maintenance? Now, check this out. For the vehicle type, we're using something called an enum. This is a special data type that basically says this field can only be one of these pre-approved options, in our case, compact, regular, or large. It's super fast and efficient. But here's the catch. It's a trade-off. It's not very flexible. If we wanted to add, say, motorcycle later on, it can be a real pain. And this right here is a classic system design decision. Do you optimize for current performance or for future flexibility? Okay, this is cool. We've got our foundation of requirements, we've built the API doorway, and we've designed the database floor plan. Now it's time to zoom out and put all these pieces of the puzzle together into a high-level architecture. So at a very high level, it's pretty simple. You've got the user on their phone or computer. They interact with our app. The app talks to our backend server. That's the brain of the whole operation. The server then talks to our database to read and write information, and it hands off the payment stuff to a secure third-party service like Stripe, because you never want to handle credit card data yourself if you can avoid it. But what happens when our app gets really popular? We have to think about scale. And we can guess that way more people are going to be just browsing for spots than are actually booking them at any given moment. So we have a read-heavy system, and we can optimize for that. Think of it like this. Our main database is the original master copy of a book. Instead of making everyone line up to read that one copy, we make a bunch of photocopies, which we call read replicas. We then hire a librarian, a load balancer, to direct all the browsers to the free copies. This leaves the line for the master copy wide open and super fast for the few people who are actually ready to check the book out, or in our case, make a book. All right, we're almost there. But let's talk about one final, absolutely critical decision. This single choice affects how our system works under pressure, and more importantly, it directly impacts whether or not a user will trust our app. And that choice is between strong consistency and eventual consistency. With strong consistency, the moment a spot is booked, it's instantly shown as unavailable to everyone, period. It's always accurate, but it can be a tiny bit slower. Eventual consistency is faster, but it comes with a risk. A spot that's just been booked might, for a split second, still look available to someone else. For a parking app, this isn't even a debate. Trust is everything. A user has to know with 100% certainty that the spot they just paid for is theirs. So we choose strong consistency. We're willingly accepting a slightly slower system to completely eliminate that nightmare scenario of two people showing up for the same spot. It's a trade-off we have to make. So how do we actually do that with all our read replicas? Well, it's a clever little trick. When someone books a spot, that's a write operation to our main database, the system sends out a signal that basically tells all the read replicas, hey, pause for a second. It momentarily locks them. Once they've all caught up and have the new information, they're unlocked. This whole process takes milliseconds, so the user never notices, but it's the magic that guarantees everyone is always looking at the absolute truth. And there it is, our blueprint for a parking garage system. From those first basic requirements all the way to critical architectural trade-offs, you can see how every single decision builds on the last one to create a robust, reliable design. So I'll leave you with a question. What if the game changed? If you suddenly had to support street parking where prices change every minute, what's the first part of this blueprint you would have to rip out and redesign? Thanks for watching.